Hello everybody, my name is Iman at SAD. Welcome back to my YouTube channel. Today we're going to go ahead and cover chapter 15. Now, there are many tools that chemists use to identify molecules and compounds. We have covered two such tools in chapter 14, infrared spectroscopy and mass spectrometry. We said infrared spectroscopy uses infrared radiation to excite the vibrational modes of a molecule and generate a spectrum of the energy absorbed by a molecule as a function of the frequency or wavelength of a light. This is a great tool for figuring out what functional groups are present in your molecule. Next, we talked about mass spectrometry. Molecules are given a positive electrical charge because an electron is deflected through ionization. The molecule then fragments into different size pieces, and the detector tallies the ions in different parts of the spectrum, and you get this mass spectrum. Now, another very important tool for chemical identification is nuclear magnetic resonance. This whole chapter is dedicated to all the intricacies of this technique. We are going to cover what NMR spectroscopy is, how it works, the 4 types of information we can extract from an NMR spectra, and how to read and understand NMR spectra for carbon-13 and hydrogen-1. Essentially, at its core, NMR gives information on the environment in which the nuclei of atoms are found in molecules and compounds. NMR spectroscopy involves the study of the interaction between electromagnetic radiation and the nuclei of atoms. It is very useful for determining the carbon-hydrogen framework of molecules. However, it's only going to work with nuclei that have an odd number of protons or neutrons, like hydrogen-1 and carbon-13. These nuclei possess a property called nuclear spin that generates its own magnetic field called the magnetic moment. When these nuclei with their own magnetic field are then placed in an external magnetic field, right? Some nuclei are going to align with the magnetic field and some will not. So let's take a nucleus occupying some arbitrarily alpha spin state, and then we subject it to a external magnetic field, to electromagnetic radiation, right? And absorption can take place if the energy of the photon is equivalent to the energy gap between the spin states. The absorption is going to cause this nucleus to flip to a different spin state. And this nucleus is said to be in resonance, thus the term nuclear magnetic resonance. So essentially, at its core, this interaction with the magnetic moment of the nuclei and an external magnetic field is in short detected by NMR to obtain the spectra we get. It is simply an interaction between the nuclei's own magnetic field and a external magnetic field that it's put in. This interaction is the reason we see and observe our NMR spectra. That is what is detected. Now, looking at an NMR spectra, there are 4 types of information that we can extract. These 4 types of information are total number of signals, right? So for our hydrogen NMR spectra, our hydrogen-1, I'm going to be calling it hydrogen or proton spectra throughout the rest of this session, so just keep that in mind. For total number of signals for our hydrogen NMR, this is going to describe how many different types of hydrogens are present. The second thing we're going to look at is chemical shift. This is going to describe how shielded or deshielded the hydrogens are. Shielded protons or hydrogens will show up at lower ppm, while deshielded protons are going to show up at higher ppm. Now, these terms shielded and deshielded, we're going to get into it along the lines, but it refers to the strength the external magnetic field protons are experiencing because of the electron. So the proton is said to be shielded if it experiences a smaller external magnetic field because of the electrons, and vice versa. Now, the third thing that we're going to look into is the height of signals or the area under signals. All right. This is going to describe the relative ratios of each type of hydrogen. And then the last thing we're going to cover is spin splitting or multiplicity. This is going to describe how close or far the different hydrogens are to each other. So let's go through these one by one, starting off with the number of signals. All right, so let's get in here. A separate flowchart for number of signals. All right, since the ultimate goal of NMR is to understand the kind of environment a nuclei is in, it's going to be important to know how many different unique nuclei you're going to observe in the spectrum. Now we're working with hydrogen NMR. So hydrogen NMR will indicate the number of different kinds of hydrogens. All right, and there are three categories for electronic environments protons or hydrogens can occupy. All right, protons that occupy identical electronic environments are going to be chemically equivalent, and they're only going to produce one signal. When two hydrogens or protons are chemically equivalent, they can be interchanged by a symmetry operation, either a rotation or a reflection. All right, so if these two hydrogens are interchangeable by rotational symmetry, they're going to be known as homotopic protons. They're chemically equivalent. So if your two hydrogens or protons are interchangeable by rotational symmetry, all right, they're going to be chemically equivalent. So you're only going to get for these two hydrogens, because they can be interchanged by rotation symmetry, you're only going to get one signal for these two hydrogens because they're not any different. They're not going to give you two unique signals in an NMR. They're going to give you the same exact single signal because they are chemically equivalent. Now, if they are interchangeable by reflectional symmetry, again, they are also chemically equivalent, but this time the term for two hydrogens that are, or two protons that are interchangeable by reflectional symmetry is enantiotopic. All right, so these two hydrogens right here, they're interchangeable by reflectional symmetry. All right, they're not going to give two unique signals on the NMR since they are chemically equivalent because they're enantiotopic. All right, they're only going to give one signal on your NMR. Now, if two protons are neither homotopic or enantiotopic, so they're not chemically equivalent, these protons are not going to be interchangeable by rotational or reflectional symmetry. These protons are going to be referred to as diastereotopic. These are protons that cannot be interchanged by any of the symmetries. They're not chemically equivalent. What that means, here's an example. Here's two hydrogens here. These two hydrogens are not interchangeable by any type of symmetry. That means that this hydrogen's going to give off one signal on your NMR, and this other hydrogen's going to give another signal on your NMR, and they're two different signals. So you're going to get two signals out of these hydrogens because they're not unique. Each one is different, and will give you a different signal on your NMR. So there's a really cool way to do a quick test to figure out, are these two hydrogens interchangeable by any symmetries or are they not? And how many unique hydrogen sites are there in my molecule anyway? All right, this is a really cool chart that breaks that down. That breaks this down. I found this online on an open source note website called Clutch Prep. They have blank notes for anyone to view, but without answers, of course. So if you want to watch the videos on their notes, you're going to have to, I think, pay some subscription fee. They're really great, but I went ahead and just took their notes and I filled them up how I thought appropriate. So this is a really cool way to figure out if two or three hydrogens are interchangeable, are they all equivalent, or if they're each going to give their own unique signal in their NMR because they're not chemically equivalent. So this method is called the replacement test or the Q test. If you're trying to figure out what the relationship of hydrogens are at a site, what you're going to do is you're going to replace one of those hydrogens by a variable group, a different group, say chlorine, all right, or bromine, or oxygen, whatever you like, all right, just replace it with something else. Now, if this test, after you've replaced the hydrogen with a new molecule, or just a Q if you want, if this test does not yield a new chiral center, then the protons are homotopic or chemically equivalent. So here's a great example, right? We're looking at this site. It has 3 hydrogens, all right? Are these 3 hydrogens chemically equivalent or not? Well, we don't know, so let's go ahead and do our Q test. All right, we're gonna replace one of the hydrogens with chlorine, for example. Cool, we did that. Now, is this a new chiral center now that we've done this? No, because there's not 4 different groups attached to this carbon. We have 2 hydrogens here. All right, we're not forming a new chiral center, and there are no other chiral centers in this molecule anyway. So if that's the case, well, then these protons are homotopic and they're chemically equivalent. That means all 3 of these hydrogens will give off just one signal. Fantastic. In general, 3 hydrogens on a methyl group are always going to be homotopic. So that's a cool fun fact that you can also just keep in mind. Now, if you do this test, if you do your Q test and it yields a new chiral center, and there are no other chiral centers in the molecule, then the protons are enantiotopic. They're still chemically equivalent, all right? But they're enantiotopic, so they have a different kind of symmetry. All right, so let's look at this example right here. All right, are these 2 hydrogens chemically equivalent or not? Well, we don't know. Let's replace one of the hydrogens with a chlorine. Cool. Now, is this site now a chiral center? Absolutely, it's a chiral center. It's bonded to 4 different types of groups. Guess what? There's also no other chiral center in the molecule, all right? So it meets the 2 criteria. We formed a new chiral center, and there are no other chiral centers. That means these hydrogens are enantiotopic. They are chemically equivalent. They share a signal. They're only going to give off one signal in NMR. Fantastic. Now, if your test yields a new chiral center and your molecule already has another chiral center somewhere else, all right, then your protons are diastereotopic, all right, and they're not chemically equivalent. So let's look at this example right here. We were trying to figure out, are these 2 hydrogens chemically equivalent or not? All right, we're going to go ahead. We're going to do our Q test. We're going to replace one of the hydrogens with chlorine. Did we form a new chiral center? Yes, we did. But guess what? There's another chiral center right here. All right, if you form a new chiral center from your Q test and there's another chiral center somewhere else in your molecule, then your hydrogens here that you're looking at are diastereotopic. They're not chemically equivalent. That means each hydrogen gives its own signal on the NMR. This gives one signal, and this gives one signal. So this is a really great way, all right, if you're not very good with symmetries, all right, if you can't tell if 2 hydrogens have reflectional, rotational, or no symmetry at all, you can simply rely on this Q replacement test, all right, and it'll really help you figure out if your protons or your protons / hydrogens are chemically equivalent or not. I mean, another way of just thinking about this is remembering a couple of other really cool notes. Your methyl groups, right? Your CH3s are always going to be chemically equivalent. These are always going to be, your hydrogens are going to be chemically equivalent. So methyl groups, all the hydrogens on that carbon only give off one unique signal. All right, and if you're dealing with CH2 groups, if there's 2 hydrogens, they're chemically equivalent if there's no other chiral centers, and they're not chemically equivalent if there is. If your molecule as a whole just has some sort of reflectional symmetry in general, like you can cut your whole molecule in half and one side looks like the other, then you can just straight up have 2 groups that are just also chemically equivalent. Like all 4 of these hydrogens are chemically equivalent and will only give off one signal. And that's only the case if your molecule as a whole has some sort of reflectional symmetry. Of course, this will make more sense when we do more practice problems. So that's exactly what we're going to do. We're going to go ahead. We're going to jump into some practice problems. All right, we're going to do a few of these. First, we're going to identify the number of unique signals each of these molecules have. All right, so we're going to take everything we've learned. We're going to figure out how many unique signals a molecule has. All right, so we're going to start off with A. All right, we're going to start off with A. We have here a little step-by-step guide that you can rely on to figure this out. All right, so we're going to draw our molecule A right here. All righty. Fantastic. All right, does our molecule, the first question we want to ask is to figure out the number of signals, right? We're going to look at this molecule and we're going to ask, is there reflectional symmetry? Is there a place where we can draw a line straight through and one side looks exactly like the other? And you can try out a couple of, like vertical or diagonal lines to see if this is the case. And what you'll figure out is this molecule has no reflectional symmetry at all. All right, so there's no reflectional symmetry for the molecule. All right, so keep that in mind. There's no reflectional symmetry for the molecule. Fantastic. Now, with that in mind, what we're going to do is we're going to observe all the unique hydrogen positions. All right, so anywhere that there's hydrogens, we're going to highlight it in orange. That's our second step. All right, so there's hydrogens here. There's a hydrogen right here. There's a hydrogen in this methyl group. There's hydrogens over here. There's hydrogens over here, here, and here. Fantastic. So we've observed all the hydrogen positions, all right? We highlighted all of them. All right, now our next step is to identify how many hydrogens are in each position. This is a methyl group. There's 3 hydrogens. All right, there are 2 hydrogens over here. This is another methyl group, so there's 3 hydrogens here. There's only 1 hydrogen here, 1 hydrogen here, 1 hydrogen here. Again, a methyl group, so 3 here and 2 over here. Fantastic. So we've figured out there's no reflectional symmetry in this molecule. Then we simply highlighted all the places where there are hydrogens, not even unique hydrogens, just places with hydrogens. All right, we highlighted them. Then we said, we wrote down how many hydrogens are in each of those positions. All right, now we're going to identify how many hydrogens there. We did that. We identify how many hydrogens are in each position. All right, so for all the methyl groups, we're going to start highlighting this in blue. For all the methyl groups, all right, there are about 3 of them, 3 methyl groups. All right, remember what we said about methyl groups. All right, all 3 of those hydrogens are chemically equivalent. What that means is we're only going to get 1 signal for each of these methyls. 1 signal, 1 signal, 1 signal. All right, now for all the positions with just 1 hydrogen, all right, nothing to do there. It's just 1 hydrogen, so that's going to be just 1 unique signal. All right, so all those positions with simply 1 hydrogen, all right, those are also going to give 1 signal. All right, so now for the positions with 2 hydrogens, now we go through our classifications, all right, to figure out whether those 2 hydrogens in each of those positions are chemically equivalent or not. All right, the hard part is figuring out if these positions with 2 hydrogens, all right, are chemically equivalent or not. So what are we going to do? We're going to go ahead, we're going to draw out both hydrogens at this position. We'll start here. Cool. Now, if we replace one of those hydrogens with if we replace it with some other molecule or atom, right, is this gonna yield a chiral center? Is this now a chiral center? The answer is yes, it is a chiral center. All right. But okay, so there we formed a chiral center. All right, is there any other chiral center in the molecule? All right, we formed a chiral center. Yes. Did we form a chiral center with our Q test? Yes. Is there a chiral center to begin with? Does your molecule have a chiral center in general? No. All right, so the molecule has no chiral center to begin with. And when we did our Q test at that position, we did form a new chiral center. What does that mean? That means that the two hydrogens over here are enantiotopic. All right, they're enantiotopic. That means they're chemically equivalent. So we only get one signal from this position. All right, now if we do the same thing at this position with two hydrogens, all right, we're going to get the same thing. All right, we form a new chiral center, but our molecule as a whole doesn't have any other chiral centers. And so that makes these two hydrogens enantiotopic, and that means they're chemically equivalent. All right, so what we've just figured out is we get one unique signal from all the methyl groups. All right, we get one unique signal from all our single hydrogens. All right, and we get one unique signal where there are two hydrogens. So how many total signals are we going to get from this molecule? 1, 2, 3, 4, 5, 6, 7, 8. This molecule is going to yield 8 signals on an NMR. All right, so this is how you can follow this step-by-step guide, all right, to figure out how many signals you're going to get on an NMR from a single molecule. All right, we're going to do one more, all right, for good measures. Fantastic. Let's erase all of this. And then go ahead and do B. All right, I'm going to go ahead and draw it right here. Oops, that's not good. All righty. Awesome. So our first question, all right, and I'm going to write it one by one so we know. Does our molecule have reflectional symmetry? Can we draw a line somewhere through this molecule and one side looks like the other? We absolutely can. If we draw our line right through those two substituents, this side looks exactly like this side. Now you might be stuck on the fact on these double bonds right here, but remember this very important fact. In a ring, these double bonds are constantly moving. Remember, we did this in resonance when we talked about resonance structures. So truly, whenever you have a ring that's conjugated like this, right, and your double bonds are constantly moving because of resonance, you can draw this ring like so. We talked about this in chapter 2 in Organic Chemistry 1, right? And so when you draw your rings like this now, all right, you can truly see how when you draw a line straight through here, this side of the molecule looks like this side of this molecule. So there is indeed reflectional symmetry within our molecule. All right, so we're going to have to write, yes, there is reflectional symmetry. Now, what does that mean for us? What that means for us is that this site is chemically equivalent to this. All right, so we only have to going to count or look at one of them. All right, not both. All right, and it means that this site is equivalent to this site. So we're only going to look at one of them, not both. All right, so keeping that in mind, all right, keeping in mind that our molecule has reflectional symmetry, let's observe all the positions with hydrogens. We're going to highlight them in green, but let's get rid of this line right through this molecule so that we don't get confused. Let's redraw it really quickly. Fantastic. All right, now we want to highlight all the positions, all right? Not double counting the ones that we said were chemically equivalent. Let's highlight all the positions with hydrogens. All right, our methyl obviously has a hydrogen, and there's a hydrogen here, there's a hydrogen here. All right, we're not going to count this or this position because they're chemically equivalent to this and this position. All right, so we're not counting that. And then this position has hydrogens. All right, so we've accomplished step 2. All right, we highlighted all the positions with hydrogens. Fantastic. All right, now our third step is to identify how many hydrogens are in each position. All right, so there are 3 hydrogens, all right, in our methyl groups. There's just 1 hydrogen at each of these sites in the ring, and this is another methyl group, so it has 3 hydrogens. All right, so remember what we talked about, all right? When there's a methyl group, all right, all of them are chemically equivalent. What that means is we're only going to see 1 signal at this methyl, and at this methyl, we're also just going to see 1 signal. All right. Now, at these 2 positions, there's just 1 hydrogen. All right. So again, for these positions, we're also just going to see 1 signal, 1 signal. There are no positions with 2 hydrogens for us to go through our step-by-step process. If there were positions with 2 hydrogens, all right, what we would want to do is ask ourselves, is there a chiral center in the molecule to start with? All right. And then you would ask, after Q-test, do we get a new chiral center? All right. If the answer to both of these questions is no, all right, your hydrogens would be homotopic and they would be chemically equivalent. If the answer to A was yes and the answer to B was yes, then your hydrogens are diastereotopic and they are not chemically equivalent. If the answer to your first question is no and yes to the second question, then your hydrogens are enantiotopic. They're chemically equivalent, so they're only going to yield 1 unique signal. All right, so our molecule has no positions with 2 hydrogens for us to go through. So again, let's do a quick count. This methyl group has 1 unique signal. This has one, and this other methyl has 1. Our molecule has a total of 1, 2, 3, 4 unique hydrogen positions. So there's going to be 4 unique signals in our NMR. All right, I hope this is helpful. Stick to this guide. All right, in case you forget how to do this, always knowing a step-by-step process really erases some of the stresses of doing problems, right? Because now you have a checklist you can always fall back onto to answer these kinds of questions, which is why I always try to implement them in my sessions, you know, having a step-by-step process to go through whenever you're taking tests. You know, don't let the stress of the test get to you. You already have a step-by-step guide on how to answer this kind of question. So just fall back onto that. I'm going to leave C and D for you to do. All right, I'll post the answers. But with that being said, we're going to move on to the next piece of information we can get from our NMR, our second piece of information, and that's the location of the signal, or in other words, our chemical shift. All right, our chemical shift describes the location of the signal. This is defined relative to a frequency of absorption for a reference compound called TMS. All right, the left side of our NMR spectra, all right, is described as downfield, and our right side of our NMR spectra is called or described as upfield. All right, upfield signals are shielded protons, downfield signals are de-shielded protons. So the signals on the left spectrum, right, are downfield or de-shielded, are called high frequency signals because they result from de-shielded protons that are going to observe higher frequencies of radiation because there are no electrons in the way to deflect some of this absorption. In contrast, signals on the right side of the spectrum, upfield, are low frequency signals because they result from shielded protons that are going to observe lower frequencies, right? Because they're shielded. All right. Now, what causes protons to be de-shielded? Well, one thing that we're really going to talk about is inductive effects that cause protons to be de-shielded. In other words, surrounded by less electron density, and as a result, the signal produced by these protons are going to be shifted downward. Right. So one of these is going to be inductive effects. We're going to see this best in this example. All right, where we observe directly the inductive effects of halogens and their contributions to the chemical shift. Now, when there are multiple halogens, this effect is going to be additive. So let's look here in our first example. All right, starting off with good old methane. All right, no halogens in this area. You're going to observe methane, all right, around 1 ppm. Cool. Now, if you add an iodine, all right, this halogen alone is going to cause a downfield shift. So now instead, you're going to see the signal at 2.2 ppm, sorry. All right, bromine, all right, also going to cause a inductive effect. Look at that. Your methane is no longer at 1.0 ppm. Because of this single bromine that we've implemented, you're going to see the signal at 2.7 ppm. Chlorine has the same effect, all right? Fluorine as well. Now, if you look at your periodic table, all right, your halogens row, all right, you have fluorine, chlorine, bromine, iodine, all right? So as you go up the halogens, all right, it's going to cause a greater shift downfield in your NMR spectra. Why? Well, these molecules, these halogens are going to have this strong inductive effect that's going to cause nearby protons to be de-shielded. Now, simply taking one of these halogens, say chlorine, all right, one chlorine is going to cause a difference of around 2 ppm shift. All right, now double it up, add 2 chlorines, all right? You're going to see, right, around a 4 ppm shift. All right, add 3 chlorines. Look how this is going to be additive. All right, adding more halogens. All right, you see an even greater effect on the shift in your NMR spectra because of these halogens. All right, so that's a really good thing to remember. All right, now in general, for some concrete numbers, all right, a methyl group is gonna show up around 0.9 to 1 ppm. All right, a methylene group, just with a carbon with 2 hydrogens on, there's going to be around 1.2 ppm. All right, and then a methane group, just a carbon with 1 hydrogen, around 1.7 ppm. Now, that's just these groups in general. What if you have other atoms nearby? All right, if there are different groups, like halogens, like we just talked about, or oxygens, right? Ester groups, ether groups. What if there's carbonyl groups as neighbors? Those are all going to cause shifts, all right, in ppm for these groups, all right? So here's a table. We see the exact effect it has on the shift when these groups are present, all right, in the alpha position, right next to. All right, the effect of these groups at a further position, at say a beta position, is generally going to be only 1/5 of the effect. All right, so what that means here is if you have this methylene group right here, right, C carbon group with 2 hydrogens, all right, you might say, oh, all right, we know a methylene group is going to show up on our NMR spectra at like 1.2, all right? Well, hold your horses. Is it next to any groups that's going to cause a shift in that signal? Well, if there's an oxygen, either in the form of an alcohol or ether, the effect it's going to have, all right, is it's going to shift by 2.5. All right, so your actual chemical shift is going to be the addition of 1.2 and 2.5. So your signal is now going to be at 3.7 ppm. All right, why? Because this alcohol group is in the alpha position right next to it. All right, now if you have, all right, here's your carbon with 2 hydrogens. If your alcohol group is not at your alpha position, not directly attached, all right, but at your beta position, so kind of like 2 atoms down right here, all right, it's not going to have a 2.5 shift effect. Instead, it's only going to be 1/5 of that. All right, so an alcohol group in the beta position is only going to have an effect of 0.5 on the chemical shift. So if your alcohol group is at the beta position, all right, your methylene is 1.2, you're simply going to add 0.5 to that, All right, so it's going to be a 1.7 ppm signal that's going to show up for this kind of structure. All right, now if you have an oxygen as part of an ester, that's going to have an effect of 3 on your chemical shift if it's directly attached, if it's in the alpha position. All right, here's your carbon. Whatever is directly attached to that carbon is your alpha position. Anything one down will be a beta position after that. All right, so if you have your methylene group right here and right next to it is attached an oxygen in the form of an ester, you want to add 3 to your 1.2 ppm. The actual chemical shift of this group right here is going to be 4.1 ppm. Now, what if next to your methylene group is a carbonyl group? All right, right next to it in the alpha position, you want to add 1 to that. So 1.2 plus 1 is going to give you 2.2 ppm. That's the chemical shift you'll observe for that. And remember the effect on the beta position. All right, this would be a beta position right here. Let's actually zoom in and assign that, right? Here's your interest, group of interest. Right next to it are alpha positions. These are alpha positions. After that is beta positions. All right, beta positions only have an effect about 1/5 of the effect as the alpha position does. So here's a little table of cool chemical shift numbers associated with different groups, right? Your methyl 0.9, methylene 1.2, methine 1.7. All right, allylic hydrogens are around 2. Alkynyl positions are 2.5. Aromatic methyls are 2.5. Okay, alkyl halides are anywhere between 2 and 4. Alcohols are anywhere between 2 and 5. All right, vinylic positions, aryl positions. So whenever you have hydrogens on an aromatic ring, you'll see that around 6.5 to 8. All right, so these are really good numbers to keep in mind. Carboxylic acids around 12. All right. Good things to keep in mind. Remember the effects of alpha and beta positions whenever you're calculating the chemical shift of each position. What we're going to do as practice is do an example. Predict the chemical shifts for the signals in the hydrogen NMR spectrum for each of the following compounds. Fantastic. So what we're going to do first here, we're going to draw A out. All right, we're going to draw A out like so. All right, we need to figure out, first and foremost, all the hydrogen signals we're gonna see before we calculate their chemical shifts, all right? So all of these methyl groups, right, we're gonna see one chemical signal from them. All right, these positions have 2 hydrogens. I'm gonna tell you, spoiler alert, if you do your Q test, if you're going to do that part, if you're going to try to figure out whether these hydrogens are chemically equivalent or not, for all of them, if you do a replacement test, first and foremost, your molecule has no chiral centers. If you do your replacement test, your Q test, you're going to make chiral centers, all right? Yes, this is a chiral center now. So as a result of these 2 facts, all these positions with 2 hydrogens are enantiotopic. And guess what? They are chemically equivalent. Cool. So we figured that out. All right. We figured out. All right. For all these positions highlighted in blue. All right. We're going to see a signal on our NMR. Let's figure out where on our NMR now. All right. So what I'm going to do is I'm going to number these positions and we're going to go through each single one. All right. So this position is position 1, 2, 3, 4, and 5. Let's start off with 1. 1 is a methyl group. All right. We see methyl groups at 0.9 ppm. Fantastic. Is there anything in here's the methyl group. So this is the alpha position to the methyl group, and this is the beta position of the methyl group. At the alpha position, is there any group like an alcohol or an ether or an ester or a carbonyl that would cause a shift, a chemical shift? No, there's nothing in the alpha position. What about the beta position? The beta position is a carbonyl. All right, so we're going to write at the beta position, there's a carbonyl. All right, now because it's in the beta position, All right, it's going to be 1/5 of the normal effect. Carbonyls cause a 1 ppm shift. It's in the beta position, so it's going to be 1/5 of that. So that's 0.2. So what we're going to add to the 0.9 is 0.2 ppm. All right, and that's going to give us a total of 1.1 ppm. This methyl group is going to show up, that signal is going to show up at 1.1 ppm on our NMR. Fantastic. Let's look at position 2 now. Position 2, all right, it's a CH2 group, cool beans, so that is 1.2 ppm, methylene. All right, now, to this group, all right, to this group, here are its alpha positions. This is an alpha position to it, and this is an alpha position. There is nothing here in this alpha position, but if you look at this alpha position right here, all right, what do we hit? We hit a carbonyl. All right, carbonyl. Oh, actually, look at that. That's actually, is that in our groups over here? All right, that's an ester. All right, so we have an ester right there. So what it's going to be is it's going to be 1.2 ppm plus 3 ppm, and that's going to be 4.2 ppm for that position. Fantastic. All right, now we're going to look at position 3. Position 3 is right over here. Actually, oops, this is a slight error. Hold on there. Hold your horses, folks. All right, this position at the alpha position is actually a carbonyl. All right, so we're going to count that first. All right, the beta position is an oxygen that's part of an ester. So that's going to be 1/5 of that effect. So 1/5 of 3 is going to be 0.6. So we're going to go ahead, we're going to add all of that up. That is going to be 2.8 ppm. Fantastic. Now, if we look at position 3, all right, let's erase some of this circling. Let's redraw this whole part right here for ourselves. Awesome. Now we're going to look at position 3. All right, here's the alpha and the alpha, all right, positions. And there's nothing in the alpha position on this side, but look over here. We have our ester right here. So this is a methylene group. So 1.2 ppm plus 3. This is going to give us a signal at 4.2 ppm. All right, then we're going to look at signal 4. All right, 4 is also a methylene, so 1.2. It's going to have this ester group in the beta position to it. So it's going to be 3. It's going to be 1/5 of that. All right, so 0.6. And that is going to give us a chemical shift of 1.8 ppm. Position 5. All right, position 5. Oh, my pen does not want to work. Position 5 is a methyl group, so 0.9. There's nothing in the alpha or beta position, so it's simply going to be 0.9 ppm. So this is the chemical shift. This is where you're going to see each one of the signals in this molecule. I'm going to let B be something that you do, and I'll post the answers. And with that being said, we're going to move into the third thing that we can learned from our NMR spectra, and that's the area under the signal, or the integration. All right, integration describes the area under each signal. This is important because it's going to indicate the number of protons giving rise to the signal. Remember, when we were counting how many signals we would expect from a molecule, we only counted unique protons. All the same equivalent protons only got counted once, right? Because they're all only going to give one unique signal. Well, how are we going to know that they even exist, though, when we look at an NMR spectra? This is where integration becomes extremely useful. Integration is going to let us know that information. So after acquiring a spectrum, the computer is going to calculate the area under each one of these signals and then display this area as a numerical value under or above each signal. All right, so it's going to integrate these signals to give us an area. All right, and we're going to get these integration values. All right, now what we're going to do here is, these integrations are big numbers. We're going to find the smallest number from these numbers, and we're going to divide all these numbers by the smallest integration value we have. All right, so for example, all right, we're going to look at this NMR signal. All right, if we integrate these two signals right here, we get 32.5 and 4.8. Which number is smaller? 32.5. So we're going to divide this by 32.5. We get about 1. And if we divide 48 by 32.5, we get approximately 1.5. All right. Sometimes you're going to get whole numbers. Fantastic. Sometimes you're going to get decimal places. If you get decimal places, you want whole numbers. So to get 1.5 to be a whole number, we can just multiply it by 2. So that gives us 3, but we have to do the same over here. So we're going to multiply that 1 by 2. All right. So what we have is, it's telling us the integration for this signal is 2. The integration for this signal is 3. All right. Remember, these are all relative numbers. Sometimes associated with the NMR, you're also going to get the molecular formula. All right. So this NMR signal is actually the NMR signal for 3-pentanon. All right. 3-pentanon, its molecular formula is actually C5H10O. All right. Now, when we integrate our NMR spectra, it's telling us 2 hydrogens are going to give off the same exact signal, right? We see it as one unique signal, all right? And the integration is telling us actually 2 hydrogens are going to give off that unique signal. And this integration tells us that for this signal, 3 hydrogens are going to give off that signal. But we know our molecular formula for this NMR spectra is C5H10O. All right, but 2 and 3, that's only 5 hydrogens that are accounted for. Well, these are only ratios. So to actually figure out, whenever we have the actual molecular formula, to actually figure out how many hydrogens are giving off these signals, all right, we're going to have to figure out what the ratio factor for both of these are. All right, so we're looking at 3-pentanon. All right, 3-pentanon has reflectional symmetry. What that means is this position is chemically equivalent to this position. All right, and this position is chemically equivalent to this position. The only signals we're going to be seeing is for this position and this position, because the other two are chemically equivalent. And we get one signal here and only one signal here because those protons in each of those positions are chemically equivalent. All right, so we're only seeing 2 total signals. That's this signal and that's this signal. All right. And then when we do the integration, it's telling us, oh, 2 hydrogens are giving off this signal in relation to position A. All right. And 3 hydrogens are giving off this signal in relation to position B. All right. But we know our molecular formula is C5H10. All right. How do we accommodate for these two? All we have to do is multiply each of these numbers by 2 to get the actual number of hydrogens giving off each of these signals. 4 hydrogens are giving off this signal. Those are this one and this one. And 6 hydrogens are giving off this signal. Those are the 2 methyl groups at each end. So having our NMR and having our molecular formula as well is really going to help us figure out exactly how many hydrogens are giving off each signal. That's going to be a very useful piece of information. All right, so sometimes the ratio only indicates the relative number of protons giving rise to each signal, and the molecular formula that is also going to be provided here is going to give the most useful amount of information, because then you can figure out how many actual hydrogens or protons give rise to each signal. This is going to take a bit of practice to really get used to. All right, piecing all these parts of the NMR signal, NMR spectra, these 4 pieces of information is really going to take some getting used to. So with that being said, let's start doing some more integration problems here now that we've discussed it. All right. So this problem says a compound with the molecular formula C5H10O2 gives the following NMR spectrum. Determine the number of protons giving rise to each signal. Fantastic. We have 4 signals here. All right. This molecular formula, this molecule gives 4 signals. All right. Fantastic. What's the lowest number here? The lowest number here is 33.2. So we're going to divide all these numbers by 33.2. All right, so this gives us integration of 1. All right, if we divide this by 33.2, it's going to give us about 1.5. This is going to give us about 1, and this is going to give us about 1.5. So what we have in order here is 1, 1.5, 1, and 1.5. We have some decimal places here. We don't want those. All right, that's not correct. So what we're going to do to accommodate for that, to get it to a whole number, simply multiply it by 2. All right, because 1.5 times 2 is going to give us 3, which is a whole number. But of course, we're going to have to do it for all of them. All right, because we can't just multiply one signal by 2. We have to multiply all of them. This gives us a new ratio, all right, of 2, 3, 2, 3. What that means, all right, looking back at our NMR signal now, after doing all of this, is that this signal, 2 hydrogens give off this signal. All right, 3 protons give off this one unique signal. All right, 2 hydrogens give off this signal, and 3 hydrogens give off this signal. Now, if we add all of these together, it totals up 10 hydrogens, and that's how many hydrogens are in our molecular formula, so we know that this is correct. So from our NMR spectra, the protons that are giving rise to each one of these signals, this first one is 2, this one is 3, this one is 2, and this one is 3. All right, let's do one more for good measure. All right, this compound has a molecular formula of C10H10O. All right, and this is its NMR, hydrogen NMR spectra. All right, determine the number of hydrogens that give rise to each signal. All right, we're going to find our smallest number. All right, 17.1, and we're going to divide all of them by 17.1. So if we divide this first one by 17, we get 1. All right, if we divide this next one by 17.01, we get about 5. If we divide this third one, we get about 1. And if we divide this last one by 17.1, we get 3. All right, so no decimal places here. And if you add them all up, they total 10 hydrogens, which is what we have in our molecular formula. So that way we know this is correct. This signal right here, 1 hydrogen gives off this signal. This signal right here, 5 hydrogens give off this exact signal. All right, 1 hydrogen gives off this signal, and 3 hydrogens give off this exact signal right here. And so this is how we use integration to figure out how many hydrogens actually give off this one particular signal in our NMR. I hope this was helpful. In our next session, we'll cover the 4th and last unique piece of information that we can learn from our NMR spectra, and that's multiplicity. And then we'll talk a little bit about carbon NMR. But for now, that's it. I hope this was helpful. Leave any questions in the comments below, and happy study.